Hello and welcome to my video on Principles of Flight. This covers most of ACP 33 Volume 2 except for the bit on helicopters, and also covers some of the heavier than air flight sections in ACP 33 Volume 1 to make it more accessible for the first class cadets as well. So, weight is the force that pulls the planes towards the centre of the earth, pulls them down out of the sky. So weight is a force that's measured in newtons. Mass is not the same as weight. Mass is the amount of matter or the amount of particles in a substance. And now gravity is the effect that changes mass into weight, and it's a force between all particles, all matter. So everything that you can pick up and touch and you need to use energy to pick up has a mass, but you are putting in energy to oppose the weight. The weight is the force which is caused by gravity acting on the mass. Just to clear up the terminology, weight out of all of those three is the only force. So the two things that affect a weight is the density of the materials you're using and how much you use of it. So if you want to make something lighter, use less of it, or use a different material. So rather than using steel, you could use aluminium. Rather than using cardboard in your design, you could make it lighter and use paper by using less of that material. Now lift is the force that opposes motion in order to keep an aircraft in the air. And we're going to talk about two different forms. Firstly, the one that the ACPs cover, but also the one that more recently NASA thinks causes the most lift, and so is more useful when we're thinking about an aircraft flying. So in the ACP model, you have your basic, very poorly drawn airfoil shape, and there's undisturbed air in front of it. Now, as the air travels over the wing, which is the same as the wing travelling through the air, some of the air goes along the bottom of the wing, and this is a shorter route, whereas a lot of the air gets pushed over the wing, which is a longer route. Now, because they're all at the same pressure beforehand, the ones on the shorter route have the same amount of air going through them, and so they're spread out like so. However, because these particles have got to go further, and there's the same number of air particles, these are actually further apart. So because the air on top of the wing is going further, it spreads the particles further apart. Now this creates low pressure above the wing and high pressure below the wing, and air wants to flow from low to high pressure, and so this creates a force over the wing as this air wants to come here. It creates a force perpendicular to the wing upwards. So undisturbed air flows over the wing. Bottom half of the wing has air moving slowly, top half has air moving quickly. Quicker air creates a low pressure. Air wants to flow from high to low pressure, which creates a force. So in NASA's model, what happens is this undisturbed air moves over the wing and is deflected down by the wing. So high camber wings or high angles of attack are going to deflect this air down. Now, as this air is deflected down, in the same way that thrust works, and so you push matter one way, and that has a resultant force on you the other way. So it's the same way rockets work. The rocket, that is a lovely rocket, shoots out a load of stuff that way, and that propels it forwards. So the wing pushes a load of air that way, and that pushes the wing upwards. So some of you might not quite have it clear in your head why the air moving over the wing has to move faster. And this can be demonstrated with any old tap. So that's your normal airflow, which isn't really disturbed by the underneath of the wing. But actually, if you constrict it, like the top of the wing does, you'll notice that the water goes quicker. And this is the same in the air. So when you constrict the flow of something, like the air, it will go faster, and that's what causes the particles to spread out, creating that lower pressure. Okay, so I'm having some difficulty getting this demonstration to show up on camera, so it might not be the best, but it just shows how when air flows over a wing shape like this, it does curve it. So you can see the air is being deflected down. You can see the little deodorant powder stuff simulating the air going through the wind as it's sprayed over it. And you can see not just how it's deflected down, the NASA theory, but also how it's a bit more spread out. Okay, so lift is not evenly distributed over the wing, so we're going to have another really terrible drawing of an airfoil shape, and we're going to represent forces with these little arrows. So this is a vector arrow, so it's got a magnitude represented by how big it is, and also a direction represented by the arrow. So the largest force acts about 1/3 down the wing. As you can hear, my dog is also very excited about principles of flight. And the other thing you need to know is that most of the lift is generated on the top surface of the wing. So there are actually little bits of lift generated by the bottom of the wing, and this is because of another lift force called downwash. So the air comes in and is pushed down by this, which creates a force down. It's not as big as this force down on top, because it's not deflecting it down as much, but there is a little force created by the bottom of the wing called downwash, which also contributes to lift. So, lift, 1/3 through the wing and mostly on the top. So in this demonstration, my finger holding the ruler up is going to simulate what the lift forces across the wing would be doing. So if I place my finger here, you can see that the ruler balances. That's because the centre of mass is acting through the same point as the centre of lift, and so there's no instability or rolling movement. If we move the centre of lift, my finger, relative to the centre of mass, then it will turn and therefore fall. So it's important when aircraft are being made that the wings, where most of the lift is, also runs along where the centre of gravity of the fuselage and engine is. Now, as the two forces, both lift and weight, are acting in opposite directions to each other, it's important that they act through the same centre of lift and centre of mass. So we know that generally the lift acts about 1/3 down the wing, so you can check that if you put your finger either side about 1/3 through the wing on the aircraft. You can check that it's balanced, that the weight is in the right place. For any plane that works, that will be the case. So there you go, that is balanced. If you try and balance it elsewhere where there isn't lift, then it's not balanced and it will fall. Same goes for the Cessna, 1/3 along the wing either side, and that will balance perfectly where the mass is, so that the mass and the force upwards from the wings act in the same place. Here's a plane that I've made and it didn't fly. I'll tell you when one does. I've taken out the engine and the propeller, so it's now, when the weight was here, is no longer here. So if we balance it on the wings, it's tail heavy. Let go of it, it falls. So not all of them perfectly balanced on the wing. It has to be designed.
Alright guys, so we're going to be talking now about thrust and drag. So thrust is what propels our aircraft forward, and drag is simply the force that opposes those forwards motions. So what drag is just the air particles bumping into the airframe and stopping it from moving forward any faster. In the same way, if you try to run through a crowd, you'd bump into a load of people and it'd slow you down. So thrust is made by pushing matter and particles backwards, and that's what propels the object forwards. It's Newton's third law. Every action has an equal and opposite reaction, so you throw something that way and it'll push it this way. So there's lots of different ways to generate thrust. Got a couple of examples for you. So here we've just got a little propeller and a motor. If we turn the propeller on, it's going to spin and it's going to push the air backwards, and you'll be able to see that when the tissue blows. So all it's doing is it's pushing the air particles backwards, and that's pushing it in the opposite direction. The other example is called a rocket balloon, and this has stretched the elastic in the balloon, and so the elastic is currently putting a force back on the air, but it's being stopped by these two paper clips. So if I remove the paper clips but still hold it shut, when I remove my fingers, the elastic will squish the air out of this end, and so it will create a force and fly off. So now when I release it, you'll see it propelled forwards. So as you can see, the air shot backwards and that propelled the balloon forwards. So as an aircraft increases its thrust, its speed increases. But as its speed increases, the drag forces also increase because it's hitting those air particles even faster. And so eventually these two forces will balance out. A certain amount of thrust with a certain aircraft will make for a certain speed. So when you increase the throttle, you don't keep accelerating, you'll accelerate to another certain speed, and I'll show you that with the Sukhoi. So I tried to demonstrate how different amounts of thrust lead to different speeds in the air, but it wasn't really working, so it was difficult to tell how fast it was going. So now the thrust is overcoming not just air resistance, but mostly drag from the floor, but it's still the same opposing force stopping the motion. So at this little amount of thrust, you can see how it travels at a constant speed-ish, depending on the train, at that speed, that slow speed. Now, if we add more thrust, it will go faster at another constant speed. And if we add even more thrust, talking to you about control and stability with this A800 glider. It's seen better days, but it still has working control surfaces. So first of all, this should all be a bit of a recap. The elevators at the back move up and down. So when it moves up, it deflects more air upwards, which creates a force downwards, like the thrust. So the force down pitches the aircraft up. Likewise, when it goes down, pushes the air down, pushes the tail up, pitches down. It's the same for all the control surfaces. So the rudder, you can see moving now, when that swings out that way, the air is being pushed more that way, it's being deflected that way, which is going to push the tail that way, and so the aircraft is going to yaw in that direction. Elevators move in opposite directions to each other. No, these are ailerons. Ailerons move in opposite directions to each other to create a rolling effect. So when it goes that way, this wing here is generating more lift, it's got more camber, deflecting the air down, and this loses lift, so the weight also pulls this round as it deflects air up, pushing it down, which causes the aircraft to roll. So it's important to add at this point that these two ways of turning, the yaw and the roll, also cause each other. So when this aircraft yaws, like that, yawing left, it actually causes this right hand wing to move through the air quicker, which causes this wing to generate more lift, and so a left yaw also generates a left bank. In the same way, if you yaw right, this wing moves quicker, and so it rolls slightly too. In the same way, if you roll, it actually turns the horizontal stabilizer so that it has a vertical component. Rather than being horizontal and generating lift sideways, it's actually now generating some lift up. So when you roll left, this actually starts generating lift, and you also yaw left. So a roll left causes a yaw left, and a yaw left causes a roll left. So both turning methods cause each other. Now the other thing is stability. So this is the ability of an aircraft to move back to its stable flight position with no input. So this aircraft is very stable. First we'll talk about the tailplane, why it's stable that way and that way. So if the aircraft suddenly moves that way, then let's say it moves that way, then this is now at an angle to the oncoming air, and so it generates some lift coming round this way. It's going to push the air this way, because the air's coming at it this way, suddenly moves, air's coming at it this way, deflects it this way, which generates a force back that way, stabilising the aircraft. So the larger the tailplane and the further away from the centre of gravity it is, the more stable. The elevator also does the same. So if it suddenly pitches up, the airflow comes and hits it at an angle. Now it's at an angle, it's going to create more lift and it's going to stabilise itself again. The other axis is also stable because we have what's called a dihedral angle. As you can see, the wings point slightly upwards, they don't come out horizontally from the fuselage. This means that if it rolls slightly, like so, this wing is now at a different angle to that wing. This wing is closer to horizontal, and so is generating more lift upwards. As you know, lift forces act perpendicular to the wing. So that's actually generating more lift upwards, whereas this is generating more lift across, which will cause a turning effect. As this wing generates more lift, it again will stabilise. So I'll say that again the other way. If we roll this way slightly, this wing is now more at an angle that way, whereas this has more of an angle this way, and so it generates more lift, turning the aircraft back, and that's called a dihedral angle. You can have the opposite of that. You can have an anhedral angle. A good example of that is the Harrier jump jet, and that's so that the aircraft can roll and do other manoeuvres quicker, because it's designed for fighting scenarios and needing to be quick and agile. So different aircraft need a different balance of stability and control. This glider is designed to be very stable. It will just fly on its own quite happily. This little model Spitfire also has a dihedral angle, so this too is quite stable, but it does have more control authority. The fuselage isn't quite so long, and it's got larger ailerons to help it roll quicker. Big commercial jets also have no need to roll very quickly, and so they are made to be very stable so that they can just fly themselves. And then of course fighter jets tend to have anhedral or no hedral, so it's just perpendicular to the fuselage so that they can roll more easily and do tighter, faster manoeuvres. So that's it for stability and control in aircraft.
The other thing I'm going to try and demonstrate today is the stability of the aircraft, which is a shocking day to do it. But if I remove all inputs, what you can note is that it keeps flying itself because it's stable. Despite being bashed around by the wind, it still flies quite nicely. I'll try and bring it closer to show you. Oh dear, this wind's really not good. So that's no input at all, just flying itself. Wind's bashing it around and it's bringing itself back to straight level flight.
A stall occurs when the airfoils in a plane stop generating enough lift to hold the aircraft in the air. There's lots of different reasons this can happen. The main two while you're in the air are your air speed and your angle of attack. If you go too slowly, the wings will stop generating enough lift and so the aircraft will begin to fall. This one's a little more complex. If you pitch too far up, then the airflow will start to separate away from the wing. So rather than getting this effect, if it goes too high, it will simply not deflect the air down as much and stop generating those lift forces. Other things that affect a stall when we're on the ground or designing the aircraft is wing damage, because this reduces the lift that it generates. Ice, because this not only adds weight but also stops the air flowing smoothly over the wing. And air density. So the higher up we go, the more spread out the air particles are, the less lift we generate, and so the easier it is to stall the aircraft. As you start off with less lift, when you lose a little bit, it makes much more of a difference. So as you can see, as the angle of attack increases, at a certain point the airflow will separate away from the wing and you'll see that lift is no longer generated. So at that point, just there, if you watch, lift and then no lift, the flow separates from the wing. I'm not sure how well that came up on camera.
Okay guys, it's not very easy with the wind today. I'm going to try and record a video for you about stall speed, but I'm really battling with the wind, so it might not be the best, so apologies for that. What I'm going to do is I'm going to fly past, gradually reduce the throttle, and eventually you'll see that I can't maintain straight level flight. Right. So 50, 40, 30, 20 starts descending. There you go. So you can see at 20% throttle, that speed it stalls. Just a bit more of a demonstration about gliding on the floor, because it was very windy when I was trying to film that, and I'm trying to fly in wind and explaining it doesn't really work. So the weight of the glider pulls it down. It will fall if we let go. So if the nose is pointed slightly down, this falling down will create air over the wings, which will create lift. So rather than falling straight down, if it points down, it will get speed and generate lift, and so it will be able to descend slowly and in a controlled way. So weight pulls the glider down, creates airspeed, creates lift, and so it flies. What about gliding? So that's where aircraft move without any thrust. And the way they do this, their weight pulls them down in order to get speed, and that speed is then turned into lift. So, all aircraft, if their engines go, they've still got weight and they've still got wings, so they can still glide. So even this Sukhoi 27 flanker, that doesn't really look like it should glide, is actually also capable of gliding. So if we're getting some height first, and I shut off the engine, so actually still keep flying around for a little bit. Now, obviously something like this isn't designed to glide, so what we have is called the glide ratio, and it's the number of distance dropped, number of distance climbed, and so something like this will have maybe a 1 to 2 glide ratio, 1 to 5 on a good day, whereas the Vikings that we fly will, their glide ratio is 1 to 35, and proper sports gliders can be as much as 1 to 50, 1 to 60, which means for every kilometre they fall, they'll be able to travel 60 kilometres. So that flight then was a free flight, a gliding free flight, which was first invented by George Cayley, and he made a stringless kite that could fly, and that's in the ACP 33 Volume 1, so it's first class stuff. So another example of a free flight glider is a paper airplane. So once it's launched, you don't have any inputs on it, it just flies itself, so I have no control over. Just a quick demo of what happens when your free flight gliders aren't balanced correctly. So I know that this requires some down input in order to glide properly, so if we launch it free flight, it's going to pitch up and stall and lose a lot of height. Equally, if we leave it set trimmed down, it's also just going to nosedive. So you could see how it pitched slightly to up. So I'd knock it down a bit more, make the nose pitch down a bit more, and it'd be good to go in the middle, and it should glide a lot better. So again, now the location of where you throw your paper plane from is quite important. Outside generally just doesn't work because they're so light. Even a really stable one with a big dihedral angle, the wind will just take it. Okay, so that's the end of my video on principles of flight, and just in case you're worried about the plane that took off from the garden, wondering whether it made it back.
Oh, brilliant.